Okay, folks, we're going to talk about exponential and logarithmic functions and how to take the derivative of those. I'm going to talk about exponential functions for a bit. Then I want you to put it on pause and I want you to try a couple homework problems with me to see if we're making progress. And then I'll have a little bit more video and we'll try a logarithmic function. Remember, natural log is the same thing as log base e. So this is the same thing as 10 log base e of 7x. And we're going to talk a little bit about what the heck e is in our discussion today and in class more than on the video. So let's go back here. Exponential functions. I was looking for a nice looking graphic on Google about, making money and how people say invest because it'll grow exponentially if you invest early in life. By the time you're older, it's going to be doing this kind of stuff. And I don't know if that is necessarily true forever, right? It always seems kind of unrealistic to me that it would just keep growing exponentially. You're going to reinvest and you're going to invest more conservatively as you get older. So, there are other functions out there that involve exponential. Like there's a beginning shape that's exponential, and then it'll flatten out into a more, when you retire and you're not making money and you're not investing anymore and you have conservative investments. So I just think, when they say exponential growth, it's not forever. And it's kind of a simplified equation, actually. I know it doesn't sound like, an exponential function could be simplified. But what I'm saying is we're studying these functions, exponential functions, because they're really honestly not that difficult to deal with. If you're talking about a real world situation where you have more complicated functions, they are more challenging to take the derivative of. So I know it doesn't feel like it sometimes, but we are trying to take baby steps, if you will. Okay. All right. So with that in mind, I want to switch over to Desmos, and I want to look at a picture here. Okay. So I made an exponential function. The base has to be a constant. And so if the base is 1, no matter what exponent, no matter like if I stick 2 in there, 1 squared is 1. If I stick 4 in there, for x, I get 1 to the 4th power. That's still 1, right? So that's why I got this horizontal line. And look at the derivative. It's another horizontal line, right? Which is 0. Y equals 0, because if you had just a constant, then the slope anywhere along here is 0, right? Now let's crank this up a little bit, okay? So here it starts looking a little bit more exponential, kind of looking a little bit more exponential. Now let me stop there for a second and let me switch back to that picture I was showing you. We are going to study this shape right here, the exponential function. We're not going to study, maybe more complex functions right now. We will later on, but we're focused on this one right here, right? So it's the red function right here definitely looks exponential to me. And I'll zoom out here just a little bit. What do you notice about its numerical derivative? It looks like an exponential function as well. So our task is going to be, to write an equation down here that would actually be, the algebraic equation for the derivative, right? Well, I would guess it's an exponential function. What is the base of that exponential function? Well, there's nothing wrong with using the base that I have right there. So I just stopped at 1.26 because we can see it's definitely an exponential function. So let me put 1.26 to the x power. Okay, well, wait a minute. Wait, not to the squared power, to the x power. You can see, obviously, that the purple one is on top of the red function. Well, the red function is the original function. The purple one is supposed to be the derivative down here. Well, it's definitely not the derivative because it's on the red function, right? You can see that, that's not the derivative. We want it to land on the green function down here. So we need some kind of modifier. So I'm going to make another slider. I'm going to call it B. And now let's see if we can lower that function. No, we don't want it to go bigger. We don't want B to be bigger than 1 because that'll vertically stretch it, right? We want to kind of compress it down there. And we want to get the purple. Oh, let's see. We're getting close, right? We're getting the purple one close to the green one. So there's some limitations with my slider, right? It's somewhere between 0.2 and 0.3. Well, let me tell you where the number comes from, okay? The natural log of 1.26. Let's see if that number is between 0.2 and 0.3. It sure is. It's 0.231 something or other. So if I change this guy to 0.23, something or other, I got too many decimal points in here, then my purple function should be right on top of my green function. So what does that mean? This is the modifier that we need on the exponential function to make it the derivative. So let me summarize that over in our notes, okay? If you have some function y equals a to the x power, then our derivative is that same function, a to the x power. Why is that? Because we get another exponential function. However, it needs a modifier on it. And that modifier or that factor that's going to vertically vertically stretch or compress the function is going to be the natural log of whatever the base is. Okay. So before we try this example down here, let's try another situation. Okay. I'm going to change the base to be the number e. And before I do that, I think what I'm going to do, since I'm not going to use a anymore, I'm going to get rid of a, and I'm going to make this e, and I'm going to put e down just so we can see it. Okay, e is 2.718. It's an irrational number, right? So let me delete this guy down here because we don't have a slider anymore. We don't have that slider. We don't need that anymore. All right, so wait a minute. I only see one curve over here. I kind of was like, wait, do I have them both turned on? So here's my numerical derivative. Let me turn the numerical derivative off and on. Wait. I thought the rule was a to the x times natural log of a. Well, what if, let's put a little like squiggly here. What if our function was not a to the x, like some random base? What if it was e to the x? E is the 2.7 number that we saw a second ago, irrational number like pi or any other irrational number. So I got y equals, the rule says I have the exponential function times some modifier, the natural log of e. Well, the natural log of e is equivalent to 1 because what is the natural log of e? The natural log of e is equal to the log base e of e. This means, what do I have to raise e to get e? So when you take the natural log of e, you're getting 1 over there. So this is really e to the x. So e to the x is the only function that is like its derivative is the same function. You don't have to have a modifier on there because that modifier that we would put on there, that factor that would vertically stretch it or compress it, is equivalent to 1. It's the craziest thing, right? Like, I mean, it's right on top of that function over there. So if I tried to create a new function like g of x, it would look the same as my f of x function. So I'm going to go e to the x, and you can see, okay, it's definitely that same function. Now this guy I think was green too, so let's change this guy to a different color, like purple. Okay, so the purple function is definitely on top of the green function. The green function is on top of the red function. So I hope I'm proving to you that e to the x derivative is just plain e to the x. So let's look down here, and I want you to put the video on pause, and I want you to try these two homework problems. Maybe you want to do this one first because that's following this rule over here, and then you do this more complicated. It's almost more complicated because it's a chain rule problem, but you do this one second. Okay, put your video on pause, try those two problems. Hey, thanks, welcome back. I'll just go in order here. So f prime of x is equal to 5e to the 3x. Okay, so I've done the derivative. I didn't start with my outermost function. So I'm going to back that up for just a second because we've been kind of doing the outermost function first. And I guess that's not true. We've been going in layers. We've been using the Bailey technique here. So you got this inner function, you got this outer function, and like it doesn't really matter whether you start with the inner function or the outer function. I'll take it back. I think we've been doing outer to inner function, and so if I was evaluating this would be my inner function, this would be my outer function. So let's go ahead and do the e to the power function first. So I get 5e to the 3x. Okay, I'm done with that derivative. I'm done with that e derivative right in there. Check mark. Now I step inside my function, that 3 to the x function, and I'm going to take the derivative of that 3 to the x, or 3x function, excuse me, and I get just plain 3. The derivative of 3x is just 3. So let's rewrite this. 3 times 5 is 15. So I get 15 start with e to the 3x. All right, let's step down here to this one. This one has a base that's not e. So we go f prime of x equals 3 to the x, and then the modifier comes into play. It's really important that you put on the factor that adjusts your exponential function to make it, the derivative, which is the natural log of whatever the base is. Okay, now why didn't I need that? I'll just say it one more time up here, because the natural log of the base is e, natural log of e is 1. So, man, I hope I'm making that clear. Those are exponential functions that, here's one where the base is not e, here's the one where the base is e. How do we deal with logarithmic functions? How do we take the derivative of a logarithmic function? Okay, well, let's think about that for a second, and let's start with y. Let me draw a little line here, because I am talking now about logarithmic functions.